Today we're going to look at the second fundamental theorem of calculus. Now the second fundamental theorem of calculus is just a re-expression or a repackaging of the fundamental theorem of calculus, which could also be called the first fundamental theorem of calculus. Now some authors, just a word of caution, some authors reverse the terminology. They call this one the first fundamental theorem, and they call the one that we already did the second one. I prefer this one because the fundamental theorem of calculus, the way I described it, to me is the more natural of the two, and this is a fitting second fundamental theorem of calculus. So I'm going to write down one way of representing the second fundamental theorem of calculus, and then we'll explore the second fundamental theorem of calculus from a few different viewpoints. So we have the second fundamental theorem of calculus. So how we can say this, we can say given a function f of x, the function defined by, so we have capital F of x is equal to the integral from a to x of little f of s ds is an antiderivative for little f of x. So i.e. capital F prime of x is equal to little f of x. So this is essentially the statement of the second fundamental theorem of calculus. Now one thing that's often confusing is that the students will see some other name for the variable f of s ds. So the variable of integration is something called a dummy variable. So a dummy variable means that it goes away. So when you have a definite integral and you integrate from one point to another point, whatever the variable of integration was, whether it's x or t or s, the result no longer depends upon the independent variable. It just represents the area under the curve between those 2 points. So, for example, if I have the function f of s or f of x, and I graph it versus x, and then over here I have f of s graphed against s, it's the same graph. So when you define a function, you define a rule that associates with every input a unique output. It doesn't matter what you call the input variable, whether you call it x or s or anything else. The function is going to be the same function. So it's just a matter of what you call it. And so if I integrate from, like, say 1 to 7, the area under both graphs is the same. So what we can conclude is that the integral from 1 to 7 of f of x dx, which is simply the area under this graph from 1 to 7, is equal to the integral from 1 to 7 of f of s ds. It's the same graph, it's the same area. So we're using a different variable for the variable of integration up here because we're reserving x to lie at, x is being used as one of the 2 limits of integration. So we're integrating from any fixed constant a to the point x. And so what the second fundamental theorem says is that when you take a function f and you integrate it from any fixed reference point to a variable endpoint, and then this is now a function of x, it's a function of the variable endpoint, that is an antiderivative for little f. So to understand this, why this is a function, capital F of x, well, for any x value, I can compute this integral from a to that given x values. So for example, if I want to do f of 10, that would just be the integral from a to 10 of f of s ds, right? So I can compute this integral between any 2 points. So the upper endpoint is simply a variable. So if I want to compute capital F of 12, I integrate from a to 12 for whatever the value of a is. I'm not fixing on any particular value. Sometimes you'll see 0 to x, sometimes you might see 1 to x, and so forth. If I want to evaluate capital F of 30, it's just the integral from a to 30 of little f of s ds. So that's why this is a function of x, because for any x value, I get a unique output. And so the second fundamental theorem of calculus says that this function is an antiderivative for little f of x. Moreover, so we'll have a little moreover, it is the particular antiderivative with the property that, kind of cramming myself here, capital F of A is equal to 0. So it's the particular antiderivative that is equal to 0 when x is equal to a. How do I know this? Well, capital F of a is going to be the integral from a to a of f of s ds. Well, the integral from a to a of f of s ds is equal to 0. So it's basically the particular antiderivative that starts off with a value of 0 when x is equal to a. Another way of writing this, so alternate way of writing this, we can say the derivative d by dx of the integral from a to x of f of s ds is equal to little f of x, right? So in the square brackets, I have my function capital F of x, and this is simply saying that the derivative of capital F of x is little f of x. So the second theorem of calculus, the second fundamental theorem of calculus really gives us an alternate way of expressing antiderivatives, and it's useful in a variety of situations. So let's look at why this is true. So why is the second fundamental theorem of truth? Second fundamental theorem of calculus. When I was in college, they used to call it FUTAC, fundamental theorem of calculus. So why is the second fundamental theorem of calculus true? Well, let's look at this expression, capital F of x is equal to the integral from a to x of little f of s ds. Now let's suppose that I have an antiderivative. So I'm defining this as capital F. So suppose I know an antiderivative, let's call it g, for the function little f, for the function little f. Right? So in other words, capital G prime of s is equal to little f of s. Well, in that case, if I treat a and x as constants, and I integrate from a to x, little f of s ds, and remember this is just the definition of capital F of x, but we can kind of ignore this right here. So if I integrate from a to x, little f of s ds, and I have this antiderivative capital G, well, I can use the fundamental theorem of calculus, aka the first fundamental theorem of calculus, to express this antiderivative as capital G of s, and then I evaluate that between s is equal to a and s is equal to x. So when I plug in x for s, I get capital G of x minus capital G of a. So if capital G is some antiderivative for little f that I know, well, the fundamental theorem of calculus says that when I integrate little f from a to x, I get capital G of x minus capital G of a. Now, capital G of a is going to be some constant value. Some constant value. So capital F of x is equal to capital G of x plus a constant. Well, when I have an antiderivative and I add a constant to it, that happens is I get a new antiderivative for little f. So therefore, capital F must also be an antiderivative for little f. Right? So therefore, capital F of x is also an antiderivative. In fact, using this formula, which describes capital F in terms of this fictitious antiderivative that I'm assuming that we can capture, we have capital F of x equals capital G of x minus capital G of a. If I evaluate this at x is equal to a, I just get capital G of a minus capital G of a, which is equal to 0. And if I take the derivative, so this one's coming back from the first line, so I take the derivative, well, it's just equal to g prime of x plus 0, because the capital G of a is just a constant, so its derivative is 0. Now g prime of x, by definition, is little f of x, because capital G is an antiderivative for little f. So that shows that capital F prime of x is equal to little f of x. So the thing to notice is that we want to use a different value for the variable of integration. Let's look at a simple example of the second fundamental theorem of calculus using some known functions. So for little f of x, let's just use something simple like 3x squared. Okay, so I'm going to define capital F of x to be the integral from, let's say, 1 to x of little f of s ds. Okay, so since we know the antiderivative of, well, we know the integral of 3x squared, we can actually compute this. So f of x is 3x squared, which means that f of s is equal to 3s squared, right? Whenever I change what's in the parentheses for f, that's the input for the function. So if I say f of x, the output will be 3x squared. If I say f of s, the output is 3s squared. If I say f of smiley face, well, that's 3 smiley face squared, just like that. So this is the same as the integral from 1 to x of 3s squared ds. So the antiderivative of 3s squared is s cubed, and we evaluate that from s equals 1 to s is equal to x. So we get x cubed minus 1 cubed, which is 1. So therefore, capital F of x would give you x cubed minus 1. Well, let's see. Capital F of 1 is clearly 0, and capital F prime of x is going to be 3x squared. So you can see we start with f of x, which is 3x squared. We change the x to an s for the purpose of the integration. So it's 3s squared ds integrated from 1 to x. And that gives us a function of x, because when we see something like this, we're integrating over s to a variable endpoint. So this quantity is a function of x, not a function of s, right? So the variable of integration is only serving a purpose as a variable while we go from the lower endpoint to the upper endpoint, just like that. So this quantity is a function of x, and that's probably one of the hardest things to understand about the second fundamental theorem of calculus. But once you understand that, you can say, okay, well, here's this function, and so the derivative is going to be little f of x. A common way that this might show up is capital F of x is the integral from 0 to x of, let's say, sine of t squared dt. So I'm using t instead of s, but it's the same thing. So the question is, we'll compute capital F prime of x. Well, it's simple. Capital F prime of x is just the function that I'm integrating, where I replace t with the variable outside, which is x. So it's just equal to sine of x squared, like that. Right, so if I integrate this function from 0 to x, and I'll have to change the variable of integration, sine of t squared dt, integrate that from 0 to x, I get the antiderivative of sine of x squared, which means if I take the derivative of this guy, I just get sine of x squared. So that's how this works.